Higher Notes, Unit 1, Section 6, Special Relativity. This is part 2, where we look at length contraction and time dilation. Let's imagine we've got the ubiquitous spaceship. Which I will draw like that. And it's got a particular length, which we'll call L. Now, I've immediately got to say, well, it says who? Well, we're imagining that we've got an astronaut on the spaceship. There he is. Okay, and we're also imagining that outside of the spaceship we have what we'll call a stationary observer. He's on the Earth. Now, if the spaceship is at rest on the Earth, so this is a very simple situation. The spaceship's just sitting on the Earth, the astronaut's inside it, the observer's outside it. What do they both measure the length to be? Well, this guy here says length equals L, say 50 meters or whatever. And you shouldn't be surprised to know that the astronaut in the spaceship says that the length of the spaceship is L. So we're both quite agreed on the length of the spaceship. Let's say it's 50 meters or whatever. Everybody agrees. Nothing really to say there, to be honest. Relativity would say that the reason both observer and astronaut inside the spaceship, when it's at rest, say that its length is L, is because they're both in the same reference frame. So if they're both in the same reference frame, then they're always going to agree on their measurement. Okay. It becomes interesting when they're in different reference frames. In other words, when one reference frame is moving relative to the other, or perhaps more correctly, the reference frames are moving relative to each other. Okay, and let's consider that. Let's consider that now. Okay, so if we call that sort of scenario 1, that's a kind of familiar one. Now look at scenario 2. So let's have our observer on the Earth. He is stationary. And now let's imagine that our spaceship is flying past. Okay. Well, the astronaut on the spaceship for him, everything is entirely normal. He just considers that the length is L, as seen by astronaut on spaceship. However, if we look at it not from the astronaut and the spaceship's point of view, but from the stationary observer's point of view, when he looks at this spaceship flying past, what does he see? Well, he actually sees a spaceship of the same thickness but shortened. Okay, and everything on it is shortened. There's the wee astronaut chap. So what the stationary observer on Earth sees is a contracted length. We're going to call it L dash. So this is the stationary observer. He sees what you might call a squashed spaceship of contracted. Contracted just means shortened. And we'll call that length L dash. Okay. Now, should have put into this diagram, incidentally, that he's travelling at speed v. And similarly here. In other words, the spaceship is travelling at speed v relative to the stationary observer. Okay. Now, it's entirely possible the physics would be identical if the spaceship were stationary and the observer was flying past, but it's simpler just to consider the chap on Earth as being the stationary one. So the question then is, if L dash, that's the length of the spaceship as seen by the stationary observer, is smaller than the length L, and L incidentally is called the proper length, this is the length that they would both agree on if everyone were stationary. What does the guy on Earth see L dash to be? Well, there's an equation and it's called the length contraction equation. And Einstein discovered that L dash equaled the square root of 1 minus v squared over c squared, v being the velocity of the spaceship relative to the observer, times the proper length L. And that equation will be given to you in the list. Okay, so let's have a look and see if we can do a simple example on that, where we'll look at a calculation. So let's imagine then that we've got a spaceship if the spaceship has a proper length L which equals 50 meters, and it moves at 0.9c relative to a stationary observer, then A what length of spaceship would an astronaut on board measure, and B what length of spaceship would a stationary observer on Earth measure. So our scenario is like this one, where the spaceship is flying past at V relative to the stationary observer. Well, the solution to part A is simply that the astronaut who is on the moving spaceship would measure its length to be L, which is 50 meters, i.e. what we call the proper length. And that's because if he took his measuring tape whilst on the spaceship to measure its length, the measuring tape would itself have contracted in length, and so he would still see the length as being the proper length of 50 meters. On the other hand, the chap who is staying on Earth, he's going to see the contracted length. So we do need to apply the length contraction equation for him. So the speed then is 0.9c. The proper length is 50. The contracted length observed by the stationary chap is the unknown. And the speed of light, of course, is 3 times 10 to the 8 meters per second. Okay. Right, so we need to state our equation. So our equation tells us that L dash equals the square root of 1 minus v squared over c squared times L. Let's put in our numbers. Well, when you're doing the v squared over c squared bit, you could put in 0.9 times 10 times 3 times 10 to the 8 on the top, and then 3 times 10 to the 8 on the bottom, and then square. But you don't need to put in all these 3 times 10 to the 8 because they're just going to cancel. So what you can do is you can just put in 0.9 there, and that's the bit that's going to be squared. Okay. Now if you look at that expression, it's the square root of 1 minus something. Okay, it's going to be quite a small something. So in fact, if we work out that 0.9 squared it equals 0.81. So you can see that the square root term is going to be the square root of quite a small number, less than 1, and that square root term will always be less than 1, basically. Okay, so if we work that out, we get the square root of 1 minus 0.81 which is 0.436 times L. So you can see that 0.436 is the square rooted term. That will always be less than 1, meaning that L dash must always be less than L, because L dash, of course, is the contracted length. So that's the 0.436 times the 50 meters. So the contracted length, as seen by the stationary observer on Earth, is 21.8 meters. A shorter length than the proper length. Okay, so there we are. That's that little shorter length there. What did we say it was? 21.8 meters. Okay, now just before we leave this problem, if the stationary observer sees a contracted spaceship, remember the principles of relativity tell us that from the astronaut's perspective, although his spaceship seems the normal length, etc., if he were to look at the Earth as he was passing it, so we imagine the astronaut to be the stationary observer, then of course he would look at the Earth and see the Earth as being contracted or squashed, and we would apply exactly the same equation but put the diameter of the Earth in there, and we'd get the same sort of amount of contraction. Right, so that is length contraction. Let's have a look now at time dilation. So time dilation is part 2 of this. I think it is part 2, isn't it? Is this part 1? No, I'm not really given it parts. That should have been 3 there actually. Okay, it's a new bit anyway. So what we're now looking at is time dilation. Worth pointing out that the word dilation means stretching. Something that's your pupils, for example, dilate in dark conditions. They stretch and get bigger. Right, I think the easiest way of understanding this one is to imagine our spaceship sort of scenario again. So let's imagine we've got the spaceship, and on board we've got our astronaut again, and next to him, standing on the Earth, we've got his twin. Okay, so we're going to imagine twins. One of them is an astronaut, and one of them is what we'll call the stationary observer on Earth. Okay, now obviously they're twins, so at the beginning of this story they are exactly the same age. Okay, let's imagine at the beginning, just to put some numbers on it, they are age 20 years, and that this guy's age is also 20 years because they're on Earth. Okay, so at the moment everything is at rest, and this guy's stationary, so he's obviously at rest as well. So they're just basically on Earth having a chat, and we'll call him twin A, the astronaut, A for astronaut, and B for the guy who's back on Earth, if you like. So twin A, the astronaut, says, right, I'm heading off now on my spaceship, and I'm going to travel quite close to the speed of light, so relativistic effects are going to kick in. Okay, so he flies off, and I'll put here some time later. Okay, and what happens is that when he returns from his trip, he lands back on Earth again, and there you've got your astronaut there. I'm back. Okay. His twin brother has been waiting on him. And the quite sort of counterintuitive thing that happens here is that the astronaut who's been away travelling at the speed of light comes back, and he measures a certain amount of time that has elapsed. Okay, so let's imagine that he's now, I'll just keep some simple numbers, aged 25 years. So he says, I've been away for 5 years. That was quite a trip. But this guy here has not aged just 5 years, he's aged considerably more. He might be, let's say, 50 years old. So this guy has become old, whereas this one is still relatively young. I say old, of course, relatively old. And that's because of the effect of time dilation. Now, one simple way of thinking about this is that for the guy in the spaceship who was moving near the speed of light, moving clocks run slow. And what that means is that the spaceship's clock, and anything which measured the passage of time, including his aging process, basically advances through time at a slower rate. So he's only advanced through 5 years of time, whereas the chap back on Earth has advanced through 30 years of time instead of 5 years. So this chap is measuring dilated time. Stretched out, if you like. Now, I think this aspect of relativity is often what causes the difficulty, because you tend to look at the guy who stayed on Earth and think, well, he's measuring normal time because he's just on Earth. It should be the guy who's off in the spaceship that experiences any strange things that might happen. But you're just going to have to accept that the language we use calls the stationary observer, as we're referring to, and remember, they're moving relative to each other. Neither of them is actually stationary. But the chap who stays on Earth, he measures the dilated time. So it's a longer time than the time measured on the spaceship. So his dilated time is t dash, whereas the proper time, if you like, is measured by the guy in the spaceship, and that's called t. Okay. I know that causes a little bit of discomfort at first, where you've got to call the dilated time that measured by the chap who stays on Earth, but you'll just have to get used to it because that's the language we use. So how do you work out the dilated time at t dash? Well, the old guy who stays on Earth, he measures t dash, where t dash is t as measured by the guy in the spaceship, divided by the square root of 1 minus v squared over c squared. Now remember from before, the square root term is less than 1. So if you divide a number by a number less than 1, you get a bigger number. So t dash will be larger than t. So let's do an example on that. Here we go. So a spaceship travels past the Earth at 2.7 times 10 to the 8 meters per second, so that's a relativistic speed. The pilot on board sees the journey as taking 240 minutes. That's according to the chap on the spaceship. Okay, he's going to measure the proper time, so that's going to be the proper time. An observer on Earth is going to see it as longer than that, but we'll come to that in a second. So, how long does an observer on Earth measure the journey time to be? Now again, we're treating the observer on Earth, as we usually do, as the stationary observer. Right, solution. Well, this is going to require a calculation, so we'll list our variables. Well, firstly, the proper time measured by the chap on the spaceship is 240 minutes. The speed of light, of course, is always 3 times 10 to the 8 meters per second. The relative velocity of the spaceship compared to the chap on Earth is 2.7 times 10 to the 8, close to the speed of light, but can't actually be it. And t dash, measured by the chap on Earth, is the unknown. Now, whenever you do these problems, you should use your sort of common sense. You're expecting t dash, as measured by the guy on Earth, to be longer. So we set up our equation. T dash equals t divided by the square root of 1 minus v squared over c squared. We put in our numbers. Let's just work in minutes. You don't need to convert to seconds because you've got time on both sides. So if you put in t as minutes, you'll get your t dash in minutes, and that's fine. Right, so that's 1 minus. Now, as before, you could put in the full speeds, 2.7 times 10 to the 8, and then 3 times 10 to the 8, but the 10 to the 8 bits are always going to cancel, so you only really need to put in the 2.7 and the 3. And remember, that's to be squared. Sometimes people forget to square that. You don't want to do that. Now when you work all of that out, check this on your calculator. You should find that the chap on Earth measures the journey to have taken 550 minutes. That is the longer dilated time. Okay, and that 240 minutes, of course, is what we call the proper time. So you've got to really accept that the proper time in these problems is the time measured by the chap in the spaceship. It's the dilated time that's measured by the chap back on Earth. And in class I will have shown you the picture of the two twins. One astronaut goes off and his brother stays on Earth, and the brother's quite old when he arrives back. And there we are. That's how you apply the length contraction and time dilation equation.